Hello everyone, my name is Derek Tu from the RIOS lab, and welcome to my presentation on my work, RGen, a tool for generating RISC-V compiler, simulator, and application support. So I think it's safe to say that one of RISC-V's greatest strengths is its modularity, allowing instruction extensions to be added to it to target a myriad of domains. This includes areas such as AI, high-performance computing, and cryptography. However, adding instruction extensions is a painful process. One of RISC-V's current blockers is the current lack of available tools for quickly translating instruction specifications to applications and code. While more mature architectures such as ARM have tools to parse their specifications, RISC-V does not, and many implementations are handwritten. So usually after writing the machine specifications, we usually add these details into different artifacts like compilers, simulators, and applications. These are all artifacts that help us realize the instruction in real-world use cases. However, this process of implementing what is written in the specification to an artifact can be the cause for a lot of headaches. It is very easy for an individual to make mistakes when implementing the instruction semantics, and there are many places where small details can trip an engineer up. Furthermore, whenever we kind of implement a target support for a target artifact, usually we have a team associated with it. And within the team, it's very possible to have mismatches due to miscommunication. And then when you expand that to an n amount of different teams working on n different artifacts with a volatile instruction specification, that spells a recipe for disaster. So all of this can result in large time sinks that would otherwise hinder the progress and implementation of the instruction extension. So our solution to this is RGen, an infrastructure for an instruction extension support. This is kind of an overview of what today's presentation will cover. Firstly, I will start off with a discussion on some basics to help build up to our decision-making process behind RGen's design. This is mainly a discussion of the different artifacts that were chosen of this work. Then I will give a high-level overview of the RGen architecture. This includes a brief explanation of RGen's extension language to SAIL RGenIR, as well as how RGen supports its targeted artifacts. Afterwards, we will discuss some basic performance evaluations based off a chosen instruction extension. Then finally, the conclusion for this work. So when it comes to RGen, there are two different categories of artifacts that we usually want to choose from. Firstly is the main machine specification that will serve as the origin point to be used for generating the code for the second category of artifacts. In this case, we have chosen the SAIL ISA as a machine specification. This is because the base SAIL language is very strong for describing instruction semantics, and through it, not only can we generate support for a lot of different artifacts. Not only this, but SAIL has been chosen as the golden model for RISC-V, so it made it an even more obvious choice. Now, we get into the second category of artifacts, which are the target artifacts. For this work, we decided to go with three different target artifacts: a retargetable compiler, a functional simulator, and a well-known application. We chose to target a compiler because for any instruction extension, a compiler is a must-have in order to compile the instructions into binaries to run. In particular, we chose the LLVM because of the retargetable compilers that are available, the LLVM has very flexible architecture descriptions. The second artifact we chose is a fast functional simulator in which the added instructions can be run and their implementations tested. We chose to support QEMU for this because it has many features to take advantage of. Lastly, we chose a real-world application which can be used to prove the usefulness of the instruction extension and set the stage for evaluating the instruction extension on the application layer. In this case, we chose PyTorch for reasons that I will go over later in the presentation. Next, I'll be going over some quick discussions of each target and how we use RGen to propose solutions to some potential concerns. So firstly, I will start off with a discussion on SAIL. Firstly, the SAIL language currently focuses on instruction semantics, so it lacks high-level definitions that can be used for describing higher-order operations. These high-level definitions are important because no matter how well designed and thought out instructions can be, if there is no support to help these instructions, test these instructions in real-world use cases, it is hard to argue their usefulness. So our solution is to add an isolated description for high-order operations to SAIL. Secondly, SAIL currently does not have some key backends that it can generate support for, which it definitely already has the ability to do so, for example, for compilers. Thus, our solution is to write these key backends using information SAIL already has. Finally, We find that while Sail's simulator can do a lot, there are some other more powerful simulators out there that we feel are better suited for testing the performance of instructions. Thus, we added backend support for Sail to generate support for these other simulators, such as QEMU. Next, I'll be giving a quick discussion on LLVM. The simpleness and flexibility of LLVM's table gen allows the LLVM to leave much of the target-specific implementations to the backend. Furthermore, since the data fields are not strictly defined in these table gen files, any new data type can be easily added to suit a new use case, as long as the associated backend is extended to support it. However, this flexibility can work against the table gen definitions, as they become more complicated to understand. For anyone new to LLVM, it can be kind of hard for them to get a quick grasp on LLVM's backend structure. Furthermore, in LLVM table gen files, there are many small instruction semantics, such as bit fields, that have to be written for an instruction, which make it very prone to small mistakes. Thus, with this work, we want to provide not only LLVM table gen definition support for compilation support, but also kind of hope that it can serve as a guide in helping users more easily use and understand LLVM. So next, I'll be giving a discussion on our chosen simulator, QEMU. So QEMU kind of suffers from the similar problems to LLVM in that it is quite complex to understand. Within its execution loop, it has another tiny code generator within it that adds a layer of complexity to it. Thus, we want to automatically generate support for QEMU, not only for it to run our design instructions, but also so that our generated support can act as a way to help new users to QEMU to understand the instruction execution process. And finally, a quick discussion on PyTorch. So this discussion of PyTorch is done in regards to a RISC-V ecosystem, as it is being used to test and validate RISC-V instructions on a RISC-V system. So the biggest issue is trying to compile the new instructions into PyTorch, as we have to compile PyTorch natively. Thus, with this work, we provide a quick and dirty way to compile the newly generated instructions into PyTorch. So now I'll be talking about our solution to all these problems, RGen. So RGen's workflow can be seen in this figure on the left side, and follows the Sail workflow where the handwritten specifications are sent to the Sail frontend for semantic checks and IR lowering, and then sent to the Sail backend for the generated artifacts. So what this work adds are a new type of Sail RISC-V definition called RGenIR, as well as extensions to Sail's frontend and backend. The RGen ecosystem has two inputs. One of them is a new language extension to Sail called RGenIR, which I will be talking about in the next slide. The other input is the base Sail RISC-V definitions that are used to describe instruction semantics. So both these input types are sent through the same compilation process and are used to generate support for the shown artifacts. The output difference between the two is that RGenIR is used to generate PyTorch support, while the base Sail language is used to generate LLVM and QEMU support. So what is RGenIR? In short, it is a language extension to Sail. So what this means is that it follows the same syntactic rules of the base Sail language. And the reason why we decided this is in order to reduce the amount of work required when modifying the Sail compilation process. So the reason it was created, I kind of mentioned this before, was because the current Sail language is only useful for describing instructions at a very low level, which sometimes does not suit our use cases. Furthermore, these descriptions can also get very long, which not only reduces readability, but also increases compilation time. So in order to introduce a way for Sail to understand high-level operations for a quick compilation, RGenIR was created. So RGenIR kind of takes inspiration from the table definition formats for MLIR, as MLIR is currently being used for many descriptions of high-level tensor languages, such as TensorFlow, ONX, and Torch MLIR. So making RGenIR easily translatable to MLIR not only introduces kind of familiarity to some engineers, but it makes it easier to support those languages further down the line. Furthermore, the table gen definitions for MLIR are concise and have a good balance between descriptable but not overly so. So these RGenIR definitions, again, are usually used to generate support for the application layer and involve generating these implementations that combine the assembly level instructions that are defined in the base Sail language. So in order to take the RGenIR definitions and use them to generate code, the Sail frontend needs to be extended to understand the RGenIR patterns and types. So these types are defined in a tree-like manner, as shown in this figure. So on the left side of the figure is the general structure of the RGenIR patterns. So these types follow a similar structure to sales-defined base types. Firstly, every declared type has two forms. The first one is the auxiliary type, which is what the CL compiler interacts with for semantic checking. The second one is the non-auxiliary wrapper that is used to ensure that each type has location information that can be used to trace that pattern node. So each auxiliary type can also have multiple patterns defined within it for type reusability and readability. And each of these patterns can consist of further high-level patterns or a base CL language, such as a string. So the right side is the tree that shows the defined RGenIR types and patterns for this work. So the leaf nodes are the base types that define most of the basic patterns. And most of the time, these are just, we just reuse SAIL-based language patterns. And the non-leaf nodes denote the higher level patterns used by RGenIR. So pattern and type checking is done by iterating through this tree and ensuring all parsed information in the RGenIR is in line with what is described within this figure. So the patterns currently used are pretty simple and are written outside of the existing SAIL patterns in order to not contaminate them. And so with that out of the way, I'll start talking about how the different parts of the three artifacts that RGen generates support for. So firstly, I'll talk about the LLVM. The part of the LLVM compiler that RGen generates support for can be seen in this dotted rectangle in the bottom area part of the figure. So the main section of the LLVM's compiler pipeline that RGen helps support is the LLVM's translation process from generic machine instructions to fully RISC-V machine instructions. So the work for this section can be broken up into legalizing the commands, selecting register banks, and finally selecting the instructions themselves. And so this is mostly done by translating the SAIL RISC-V definitions. And so helping LLVM understand how to legalize and select which instructions can be achieved by introducing the full instruction semantics, such as bit fields, mnemonics, and argument string format. And helping LLVM understand how to select certain register banks can be achieved by creating these register banks within the LLVM definitions and associating them with the added instructions. So to add support for the LLVM, all RGen needs to do is generate an instruction format table gen definition, a scheduler table gen definition, and instruction information table gen definition. So I don't know how many people know what a SAIL definition looks like, but usually they have instruction semantics and execution code. And the instruction semantics defined in the SAIL definition are what we use to generate the instruction format table gen definition, because we want to use the bit level information in order to generate the details required for the instruction format. Within the SAIL definitions are also what are called instruction mnemonic information, and this is kind of like what you see when you see the assembly level stuff. So this kind of mnemonic information is used to generate instruction information and scheduler table gen definitions. And it does so by translating the instruction mnemonic and instruction argument strings into an LLVM understandable format. So then after generating these table gen files, they're added to the LLVM source code, and we rebuild LLVM, and basically the LLVM is able to create compiler tools that will help us compile, and they will understand these newly added instructions. So next I'll be talking a bit about QEMU. So the section of QEMU's execution loop that RGen needs to generate support for can be seen in this colored area in this figure. So supporting QEMU requires extending the adding to the decoder as well as QEMU's inbuilt code generator, the tiny code generator. So this is done again by translating the SAIL RISC-V definitions. So generating support for QEMU's decoder requires RGen to translate over the instruction semantics, such as its bit fields, as well as the instruction mnemonic. So and then generating support for QEMU's tiny code generator requires RGen to, again, use the SAIL RISC-V definitions to set up tiny code generator translation functions, as well as some associated helper functions in order to allow the instructions to manipulate the emulated CPU state. And so in order to add support for an instruction to QEMU, we need to generate instruction decode information and instruction functionality information. So taking from the SAIL RISC-V definition, its instruction decode information is used to generate QEMU instruction decode information. And it helps with QEMU's instruction decode logic, where the bit information is directly grabbed and translated to a format that QEMU understands. The instruction execution information from the SAIL definitions is used to generate QEMU execution code. And so execution code lines are usually translated mostly one-to-one with very little optimizations done in order to ensure simplicity with the translation logic. And these generated files are added to the QEMU source code, and then the newly compiled QEMU will be able to execute the new RISC-V instructions. And so the section of the PyTorch's data flow and interface that RGen must generate support for can be seen in this dotted rectangle area in this figure. In particular, these are the PyTorch Python API generator and C++ backend. And so these are all done using the RGenIR definitions. And so unlike code generation for LLVM and QEMU, PyTorch uses RGenIR generated ASTs for operator definitions, as it does not need to know instruction level semantics. So for RGen to offer PyTorch ops support, it needs to generate the API-facing operator descriptors, which are inserted into a YAML file for API generation and the associated C++ implementation for each operator. So next, I'd like to present our performance and evaluation of RGen. However, before we go there, I'd like to mention that I would explain why PyTorch was chosen as our target for the application layer. So the main reason we chose PyTorch is because of the extension we chose to test RGen. The extension we chose to test RGen with is the matrix extension, which is fairly new to the RISC-V environment. And this is a very simple version, kind of loosely based on Johnson and Colley's work on the Apple AMX instructions. They're not very official, and they were kind of just used to test the whole pipeline process of this work. So with that out of the way, I will go over how we tested RGen. So after RGen is used to generate support for LLVM, QEMU, and PyTorch, the generated files are added into the respective artifacts, while some of the generated files are added into the artifacts directly. Some of them have to be cross-compiled. For example, PyTorch's support have to be cross-compiled later on and added later on. So these two tables kind of show the ratios of generated per handwritten lines of code. So the top table is the ones for the lines of sale definition to LLVM and QEMU. And I'm out of time, but basically we can do this in less than 20 minutes, and the operations run pretty quickly. And if people want to take a picture of this real quick, it's all on GitHub. Thank you.
All right, let's give him a big hand.